Okay, let us begin our lecture. So this video is on the calculation of the heat of reactions. So as you had learned from your thermodynamics in last year that it is actually a study of energy change whereby it's either internal energy, enthalpy or work. Okay, for a reacting or non-reacting system. In the past previously we have been looking at a non-reacting system. So in this module we'll be looking mainly on the reacting system. So it does give you important information like for example the heat liberated or absorbed during the reactions and the maximum possible extent of the reactions. So for this it means that it's either it's an exothermic or it's a endothermic reaction. Okay, so the other thing is that chemical reactions are always accompanied by the liberation or absorption of heat. So that's why some reaction you can see is a very violent reaction, it generates a lot of heat. Or if not, you can see that the reaction actually turns cold over time as the reaction proceeds. So for any chemical reactions that between the stable molecule species, so when two molecules they react, so energy is absorbed, right, to break the bond. Okay, or when it's released when new bonds are formed. So for instance, it's like this. So if this is a molecule of A and B, and when this bond is break, okay, this will give out heat. Wrong. So heat will be taken in. However, if a new bond is formed, heat will be given out. So in chemical reaction, a delta H is always written as heat. So therefore, with this, right, it's important for us to calculate the standard enthalpy of reactions or heat of reactions because it is actually defined as the energy that is transferred from the surrounding under standard conditions. So it can either be a positive or negative value depending on whether it is a endothermic or an exothermic reactions. So I mentioned earlier that standard heat of reaction is defined by this delta HR. So the R stands for the reaction is a heat of reaction, and this symbol over here is called phi. Phi is defined as under standard condition. Standard condition is 298 Kelvin and 1 atmospheric pressure. So in order to determine the standard enthalpy, the reactant system must be always at the same temperature of pressure. So before, after the reaction. So we must make sure that like your reactant and your product, we are talking about it, is at the same temperature, even though the reaction actually proceed in the exothermic fashion, such as the final reaction can actually be even more, has contained more, a higher temperature than the initial state. So we can apply the Hess law. There's something called the Hess law, where the heat of reaction is calculated by a generic form. So for example, this A plus B to give me C plus D. So the heat of reaction is the heat of C plus the heat of D minus the heat of A plus the heat of B. So this, if you realize, is your product, whereas this is your reactant. And the F over here stands for formation. So similarly, under standard condition. So what does all this mean? It means that it's actually the heat of formation of the product minus the heat of formation of the reactant and the sum of it. So just like this. This is the general equation. So we have two different forms. One is using the heat of formation. For this case, this is heat of combustion. So when do we use which equation? It depends on what is the data that is given to you. If let's say you are given the data of the heat of formation table, so we will use this equation. Otherwise, this is for heat of combustion. So no matter what, you must be consistent that if you use the heat of combustion for reactants, and the product must be the heat of combustion as well. There are things to take note. This is reactant first, but if you use formation, the product will be first. So do take note of this and do not get this mixed up. Otherwise, your sign will be different. So let's look at one example. It's given your lecture notes. Calculate the standard heat of reaction delta HR for the combustion of methane. So hopefully with this example, we can actually give you a better idea on how to solve this kind of questions. So this is methane. So first of all, we must make sure that it is balanced. So CH4 plus 2O2, and if you realize that this is actually 2H2O liquid form. So do take note that it's a liquid form because it plays an important role. Later we can see. So with this we see that the equation is balanced. So how are we going to solve it? The table that is given at the back of this chapter and the appendix says that it's a standard heat of formation of common compounds. So we will use the heat of formation. So you want to use the heat of formation to calculate. So heat of reaction is the sum of my heat of formation of my product minus the sum of the heat of formation of my reactant. Okay, so what we're going to do is we can go to the table and find what is the heat of formation for all this term. So we can do it one by one. So let us find the reactant first. CO2, gaseous state. So CO2 is over here, has a value of negative 393.509. Okay, note the unit is kilojoule per mole over here. So heat of water, and it's in liquid form. See, it's over here. You'll notice that there's actually two water over here, but one is a gas, one's a liquid. So we are looking the one in liquid form, which is negative 285.8. kilojoule per mole. And with the product found, we need to find the reactant. So for CH4, methane, is over here at negative 74.9. And lastly is for oxygen. Oxygen itself is an element. So for elemental species, it's very straightforward. The heat of formation is 0. So to take note of this. Okay, so we have all these values over here. Let us calculate the heat of formation, which is product. We will have CO2 2 times of water. Okay, minus of the reactant, which is plus delta H of oxygen. So to take note that there is a to take note of the coefficient over here. So why we have a 2 and 2 over here is because we need it from a balanced equation over here. The coefficient is 2, so that's why we need to include it over here. So for CO2 is minus 393.509 kilojoule per mole plus 2 times water is 285.8 minus CH4 is negative 74.9 and plus 2 times 0. This is for oxygen. So if we solve this question over here, solve this equation, you get a value of negative 890.2 kilojoule per mole. So I want to bring your attention to this point, this sign over here. This is a negative value. So this is less than 0. So less than 0. So you can see less than 0, it means it's an exothermic reaction. So you can expect that this reaction will give out heat. So if you look at it, yes, it's expected because this is a combustion of methane. So it's like a combustion of fuel. So definitely you can generate a lot of heat out at 890.2 kilojoule per mole at standard condition. Okay, so let's look at the next question example from this chapter. So magnetite is used to oxidize aluminum to form aluminum oxide. So balance the equation below and determine the standard heat of reaction during this process. So let's begin by balancing the equation over here. So this 1Al is over here, so we can put half over here. So if you want to calculate the heat of reaction, is okay if it's a non-integer coefficient. So if this is 3, there's a 3 over here. So we're going to state 1 mole of this to we want to calculate the heat of reaction for 1 mole of magnetite over here. Then we can proceed to balance it. So if we have 3 over here, so this is 4 over 3, and this 4 over 3, this will be 8 over 3. Yeah, this is the balance equation over here. So when we balance in this, you realize that there are some non-integer value over here. So the reason is because that we want to find for 1 mole of magnetite. So with this we can find the heat of formation, okay, of aluminum oxide. So aluminum oxide is over here, negative 1669.8 kilojoule per mole. And heat of formation for iron, same as before, because this is an element, so you expect it to be 0 kilojoule per mole. Heat of formation for aluminium is 0 kilojoule per mole again, because it's an element. So for magnetite, is over here, Fe3O4, negative 1118 kilojoule per mole. So the heat of reaction will be the heat of formation of your product minus the reactant. So for this, I'll just write those that involve. Minus four over 3 times 1669.8 kilojoule per mole minus 1118 kilojoule per mole. And if you work it out, it will be negative 1108.4 kilojoule per mole.